Now we're going to discuss the concept of the moment of a couple. Two forces, F and minus F, having the same magnitude, parallel lines of action in opposite sense, form a couple, as shown in figure 3.25. The sum of the components of the two forces in any direction is 0, and the sum of the moments of the two forces about a given point is not 0. The two forces make a rigid body rotate, in this case counterclockwise. What makes the rigid body rotate is that minus F and F are separated by a certain distance. If the two arrows are back to back, then they'll just cancel each other and there wouldn't be a moment. The position vectors of the points of application of F and minus F are R sub A and R sub B respectively, as shown in figure 3.26. Here's R sub A, here's R sub B, minus F and F, and there is the resulting moment M about the origin of the forces F and minus F. The sum of the moments of the two forces about the origin is R sub A cross F plus R sub B cross negative F, and that equals R sub A minus R sub B cross F. If we let R equals RA minus R sub B, then the moment of the couple M equals R cross F. D is the perpendicular distance between the lines of action of minus F and F, and the magnitude of the moment is equal to magnitude of R times magnitude of F times sine theta. There's theta, that's the angle between R and F. And that just equals the magnitude F times the distance D. Here's some real-world examples of moments of a couple in action. Every time you drive a car and you turn left, the force has to go up on the right side of the steering wheel and down on the left side. These two forces are separated by a distance D. They make the steering wheel move counterclockwise and the car moves to the left. And if you've ever had the misfortune to get stuck on the side of the road and have to change a flat tire, you're using a tire iron, in which case this socket goes into the nuts on the tire. In order to tighten the nuts, you would rotate the tire wrench in the clockwise direction. You would do this by applying a force F up on the left side, a force F down on the right side, and the moment would be equal to D times F. If you had to loosen the nuts, then you would have a force F going down on the left side and a force going up on the right side. Here's some other moments of couples in action. Here's Woody and Jessie fighting for food. It was supposed to be Woody's food, but Jessie does not have good table manners. She shoved his head out of the way and started eating. Here on the bottom, we have elderly baby boomer couples sharing a romantic moment at the beach. This one hurts. I'm a baby boomer. You can have equal moments of two couples as shown in figure 3.28. One consisting of force F1 and minus F1 in this upper plane, and the other of forces F2 and minus 2 in this lower plane. The moments will be equal if they lie in the same or parallel planes. We're showing parallel planes in figure 3.28. They have the same sense, and the moments have the same magnitude, which means F1 times D1 is equal to F2 times D2. In homework problem 3.70, we'll determine the moment of a couple. Two 80-Newton forces are applied at corners B and D of a rectangular plate. The forces form a couple separated by a certain perpendicular distance, and our job is to find the moment of a couple. We can do this by choosing either point B or D as a pivot point, take the components of the force that does not go through that pivot point, and multiply by the perpendicular distances to find the moments. Here's how we do it. We'll take this 80-Newton force on the left and resolve it into horizontal components S and vertical component T. S equals 80 newtons times the sine of 50 degrees, which equals 61.3 newtons. T going down equals 80 newtons times cosine of 50 degrees, and that equals 51.4 newtons. Now with these two forces, we can sum the moments around point B, and that's equal to force T times 500 millimeters, which is half a meter, minus force S times 300 millimeters, which is 0.3 meters. The moment of force T is positive because it wants to make this rectangle rotate around point B in a counterclockwise direction. And the moment of force S around point B is negative because it wants to make the rectangle rotate around point B in a clockwise direction. When you do the math, you find that the moment equals 7.32 Newton meters in the counterclockwise direction. With the moment determined, you can find the distance from the moment just by dividing by one of the forces. D, the distance, is equal to the moment divided by 80 newtons, and that equals 91.6 millimeters. In reality, we didn't need to calculate the moments of these couples in order to determine distance D. We could have done it purely by geometry and trigonometry. But that wouldn't be fun. This is a class on vector mechanics. You can add couples too. The couple in plane P1, which is this horizontal one, consists of F1, here's F1, and minus F1, acting perpendicular to the line of intersection of planes P1. That line of intersection is shown by vector R. The couple in plane P2, which is angled with respect to the horizontal, consists of forces F2 and minus F2, and they also act perpendicular to the line of intersections of planes P1 and P2. The resultants are of F1 and F2, so here's R, and then there's the resultants negative R of minus F1 and minus F2, also form a couple. And the moment of that couple, M equals small r cross large R, which equals small r cross F1 plus F2. Using Varignon's theorem, M is equal to R cross the sum of F1 plus F2, which equals R cross F1 plus small r cross F2, where small r cross F1 equals M1. Here's M1, and that is the moment of the couple in plane P1. And small r cross F2 equals M2, and that's the moment of the couple in plane P2. And the sum of two couples of moments M1 and M2 is itself a couple of moment M. And moment M is equal to the vector sum of M1 and M2. Couples obey the law of addition of vectors, as shown in figure 3.33a. Arrows used to represent the couple are considered a vector too, as shown in figure 3.33b. So here's our arrow, and then there's a little counterclockwise arrow going around the linear arrow. And this vector M is known as a couples vector with this extra symbol of a counterclockwise arc going around it. A couple vector, like the moment of a couple, is a free vector, which means you can show it as its own vector M with the little counterclockwise arrow around it, as shown in figure 3.33c, or you can go to figure 33d and you can devolve it into mx, my, and mz, where each of these vectors is its own couples vector, respectively located on the x-axis, the y-axis, and the z-axis. Here's homework problem 3.72, in which we add moments to determine the forces of a couple. A multiple drilling machine is used to simultaneously drill 6 holes in the steel plate shown. Each drill exerts a clockwise couple of 40 pound-inches, and there's 6 of these clockwise moments that occur because there's 6 holes. And our job is to determine an equivalent couple formed by the smallest possible forces acting on the plate. So the moments on the 6 holes will be added to create one big moment, and the large moment can be moved anywhere on the plate. The smallest forces will have the largest radii. The largest radii will cut across line BC because that's the longest distance on the plate. Here's our calculation. The moment M, which is in the clockwise direction because we're trying to drill holes, and when you drill holes you always drill in the clockwise direction, can be added 6 times to get the total moment 240 pound-inches in the clockwise direction. Small d is just the square root of 12 squared plus 16 squared because it's the diagonal distance between C and B. And we imagine these forces F of the couple are acting at points B and C respectively, perpendicular to the line that connects B and C. Then we take our 240 pound-inch moment and divide by 20 inches, which is the length of line BC, and we get that 240 over 20 is equal to 12 pounds. Now we'll discuss how to resolve a given force into a force at the origin of the rigid body at point O and a couple. Force F acts on a rigid body at point A as defined by position vector small r. We can't move F from point A to point O without modifying the action of force F on the rigid body. And the reason is that points O and A don't lie in the same line of action. But one thing we can do is attach 2 forces at point O that counteract each other. A force F acting parallel to our original force F, and a force negative F acting in the equal and opposite direction, because the net force of F and minus F is just 0. Now we keep the force F that's applied by O, and we create a couple of the forces plus F acting at point A and minus F acting at point O. And the moment M sub O is equal to R cross F. And we show that moment couple M sub O as having this extra clockwise direction arrow around the moment arrow. So in sum, we've moved force F from point A to point O by adding a moment that represents the cross product of small r, which is the vector pointing from O to A, and force F. The combination of the force and the moment acting at point O has the same effect on the rigid body as the original force acting at point A. Another way of saying that is that the couple imparts the same rotational motion about point O that F produced before it was transferred from point A to point O. M sub O is perpendicular to the plane containing R and F. And here we show M sub O perpendicular in figure 3.34c. You can apply M sub O anywhere because that is the nature of moments. You can move them around, but we usually attach it at point O together with point F. And the combination of M sub O and force F is called a force couple system. Homework problem 3.81 will show us how to resolve a force into a force and a couple. A 500 Newton force is applied to the riveted plate assembly. The assembly is riveted at points A and B, and I'll outline here in my mouse that's one metal part, and this is the other metal part that sort of looks like a pot, but a pot without a side on the right. Our job is to determine an equivalent force couple system at point B, knowing that a force of 500 newtons is applied all the way on the right edge at a 30-degree angle to the vertical. First, we'll define a vector F for the 500 Newton force in terms of I and J. Then we'll define the radius R sub B that extends from point B to the point of application on the right end. We will calculate vector M sub B, and that will be equal to R sub B cross F. And then we will move our 500 Newton force from the right edge to point B. We resolve our 500 Newton force into xy components by noting that magnitude F times sine 30 degrees is the x component, and that's 250, and magnitude F times cosine 30 degrees is the y component, so that's cosine 30 degrees times 500, which is minus 433 newtons in j direction, and it's minus because this force F substantially points downward, given that our y-axis points upward. R sub B is equal to 0.3 times I minus 0.175 times j, where we use meters as the units of measure. It's 0.3 in I because this point here on the right is 300 meters to the right of point B, and it's minus 0.175 in J because the point here on the right is 175 meters below point B. When we take the cross product of R sub B and F, we get that M sub B is minus 86.2 Newton meters in the k direction, which means it's a clockwise moment. And here's our revised diagram, where we now have our 500 Newton force acting at point B at a 30-degree angle to the vertical, and we also have a moment of minus 86.2 kilonewtons. In sample problem 3.6, we'll resolve two couples into one couple. Using the diagram on the left, we're going to look for ways to add equal and opposite forces to those in the diagram so that we can create new couples. These new couples will have moments along the coordinate axes. Then we're going to combine our new couples into a single equivalent couple. The easiest way to do this is to attach two equal and opposite 20-pound forces at point A. We can do that because the 20-pound forces cancel each other. On top of that, the 20-pound forces are going to create two new couples. I'll show you with my mouse. We've got this 20-pound force acting in the negative x direction at point A, and that will create a couple with this 20-pound force acting in the positive x direction. This 20-pound force acting in the positive x direction at point A can be coupled with this 20-pound force acting in the negative x direction at point E. Now we have to represent the three resulting couples by vectors m sub x, m sub y, and m sub z, which are directed along our coordinate axes. To calculate the moment around the x-axis, we take our 30-pound force acting at point D in the positive z direction, couple it with our 30-pound force acting in the negative z direction at point C. They're 18 inches apart. Minus 30 pounds times 18 inches is a minus 540 pound-inch moment around the x-axis. To calculate the moment around the y-axis, we take our 20-pound force acting in the positive x direction and couple it with this 20-pound force at point E acting in the negative direction, and they're 12 inches apart. 20 by 12 is 240 pound-inches. The direction of this moment around the y-axis acts in the counterclockwise direction, and hence it's plus 240 pound-inches. For the moment about the z-axis, we couple these 20-pound forces at point A and point D, which are separated by 9 inches. Multiplying 20 by 9, we get 180 pound-inches, and the reason that's a positive moment around the z-axis is that these two forces combine to make a clockwise moment going around the z-axis. Picture on the lower right shows that we can move the moments from their original position along this assembly and move them acting along the coordinate axes. Because unlike forces, moments can be moved in space as long as where you move them is a parallel axis. In step 3, we verify the solution by computing the sum of the moments of the original 4 forces about any point. And we choose point D because 2 of the forces act at point D and will have 0 moment. We need to calculate the moment of this 30-pound force with this position vector r sub dc, and we need to calculate the moment of this 20-pound force acting at point E with the position vector r sub de. 18 inches in J is vector r sub dc because point C is 18 inches above point D. And it's a minus 30-pound force in K because this force is acting along the negative z direction. R sub dE is a vector that is plus 9 inches in the J direction because point E is 9 inches above point D in the Y direction. And it's a minus 12 inches in K because point E is 12 inches closer to the origin than point D is. So you have to go in the minus z direction to get from point D to point E. We find that the 18 inches in J crossed with the minus 30 pounds in K will be a minus 540 times I because J cross K is equal to I. So there's our first term, minus 540 in I. Then we take 9 inches in J crossed with minus 20 pounds in I, and that's minus 180 times J cross I. And looking at our chart here, J cross I is a minus K, so minus 180 times minus K is actually a plus 180K. Our third term is minus 12 inches in K crossed with minus 20 pounds in I, which is plus 240 pound-inches times K cross I is J, so that is a plus 240 in J. And if we look at what vector that we get, minus 540I plus 240J plus 180 in K, that's the same vector that we did get in step 2. Before we go to our next example, I got a little worried that perhaps these moment problems are getting tedious. So I decided to consult with my wise one, Oliver, see what he thought. I said to him, Oliver, is this getting tedious? Should we move on? And here's what his thought was. In sample problem 3.7, we will replace a force and a couple by a single force. In the lever shown, this lever has a 400 Newton force acting down at point B, and it's got a couple of 200 newtons to the right, 200 newtons to the left, which will create a moment around point O, where the wheel has a 60 millimeter radius. We'll also determine the distance from the shaft to the point of application of the equivalent force, meaning if the current force, 400 newtons, is 300 millimeters between point O and B, we'll find what is that new distance for our equivalent force. Step 1, we have to calculate the moment of the 200 Newton couple. And then we'll move our minus 400 Newton J force to point O, and then we'll add a couple of moment M sub O equal to the moment about O of that force. The 200 Newton forces will create a couple of moment F times D, where F is 200 newtons, and D, the distance between these two forces, is 2 times 60 millimeters, or 0.12 meters. The moment of that couple is minus 24 Newton meters in the k direction. In order to calculate the moment of this 400 Newton force around point O, we take the cross product of our vector OB with our force F. Vector OB is 0.15 meters times I plus 0.26 meters times J. The J value is obtained from the fact that 300 millimeters times the sine of 60 degrees gives the Y distance between point O and point B. When we take OB crossed with F, we have 0.15 meters in I crossed with minus 400 newtons in J, which gets minus 60 Newton meters in K. And the second term, which is 0.26 meters in J crossed with minus 400 Newton meters in J, is 0 because J cross J is 0. Then we can move our force F of minus 400 newtons from point B to point O and add that minus 60 Newton meters in K moment. So now we have two moments, a minus 24 Newton meters in K moment and a minus 60 Newton meters in K moment, and we have one force at point O, which is minus 400 newtons in J. But moments can be added, and it's easy to add moments when they have exactly the same direction. Minus 24 minus 60 is minus 84 Newton meters in the K direction. And now we can show a minus 84 Newton meters in the K direction and a minus 400 newtons in the J direction acting at point O. Now we have to find where along this shaft we locate point C such that a minus 400 Newton in J force at point C will create a minus 84 Newton meter couple in the K direction. So we show the equation minus 84 Newton meters in K is equal to vector OC crossed with F. And we don't quite know the magnitude of vector OC, but we do know that it's angled 60 degrees relative to the horizontal. So we show OC as a variable times cosine 60 degrees in I plus OC times sine 60 degrees in J, and we take the cross product of that with minus 400 newtons in J. Has to equal minus 84 Newton meters in K. Now when we take the cross product of an I plus a J times a J, the J cross J product is going to be 0. So we're left with the fact that minus 84 Newton meters in K is equal to a minus 400 times OC times cosine 60 degrees in K, which means that OC times cosine of 60 degrees is 84 divided by 400, which is 0.21 meters, and cosine 60 degrees is a half, which means that OC is equal to 420 meters. So in summary, we were able to take our original force of 400 newtons and our 200 newton couple and change the position of where that 400 newton force was from point B to point C, which then eliminated our 200 newton force couple. This is actually a more direct method to calculate the new location needed for the force, and that is if you have to go from a point B to a point C, and you know at the start what is the moment at point O, which was minus 24 Newton meters in K, we figure out what's the distance directly between B and C to eliminate a minus 24 Newton meters. So we're solving now for the vector BC, and we say that minus 24 Newton meters in K is equal to BC cross F. And we get that minus 24 divided by 400 is equal to BC times cosine 60 degrees. And minus 24 over minus 400 is 0.06 meters, or 60 millimeters. And 60 millimeters divided by a half is 60 times 2, so that BC is 120 millimeters. So the distance from O to B was 300. We add another 120 millimeters, and we see that OC is 420 millimeters. And we can do the whole problem in one step. Let's discuss how to, in theory, to reduce a system of forces to an equivalent force couple. In figure 3.36a, forces F1, F2, and F3 act on a rigid body, respectively at points A1, A2, and A3. And we have three position vectors that connect point O to our 3 points, A1 and A2 and A3. And these position vectors are given the names R1, R2, and R3. We can move each force to a given point O, in other words, from A1 to O, or from A2 to O, or from A3 to O, if we add a couple of moment m sub I equal to the moment r sub I cross f sub I of force f sub I about point O. And that's shown in figure 3.36, where we moved all three forces to point O, but in order to do that, we had to create three moments, m1, m2, and m3, where m1 is r1 cross f1, m2 is r2 cross f2, and m3 is r3 cross f3. And once all the forces are acting at point O, you can add the three forces vectorially and create resultant r, and you can add the three moments vectorially and create moment m sub O of r. So we started out with three forces acting at three different points, and we wind up with one resulting force at point O and one resulting moment vector at point O. And note this notation, m sub O, where r is a superscript. That means that you got a series of moments by moving forces from different points to point O, and then you added up all those moments to get one moment. And vector r means you moved forces F1, 2, and 3 to point O, and then you added up those three forces and got resultant vector r. We can also replace a system of forces and a couple at point O with a force and a couple at another point O prime. So we just calculated this resultant force r and vector m sub OR at point O, and now we want to move it from O to O prime, knowing that vector s connects O prime to O. The resulting force r will remain unchanged, but now we're going to get yet another moment. And the new moment is called MO prime of r, and that's equal to our moment m sub O of r plus s, which is our position vector crossed with r. And that's what we get in the lower right corner, where we still have vector r, but now we've got a new moment that we have to calculate. Here's an example of how to reduce a system of forces to an equivalent force couple and then move the force couple. A 4.8 meter long beam is subject to the forces shown at the bottom. So there's four forces. There's 150 newtons and 100 newtons act up, 600 newtons and 250 newtons act down. And we need to reduce the given system of forces to an equivalent force couple at A, an equivalent force couple at B, and a single resultant force R, which acts at a strategic location that it will create a zero moment on the beam. And note, because the reactions at the supports are not included in our given system of forces, the given system will not maintain the beam in equilibrium. Meaning, as we move forces around, the beam's going to go flying, but don't worry about that part. Now, the force of an equivalent force couple system is the sum of the forces involved, which is easy enough to sum because they're all going in the y direction. And the couple is the sum of the moments caused by each force relative to our point of interest, which is either going to be A or B. And once we find that equivalent force couple at one point, and we'll start with point A, then we'll be able to transfer it to another point by doing the moment calculation of the original force crossed with the position vector that connects A and B. In step 1, we will define the force couple system at A that it's equivalent to the given system of forces. Doing the force calculation is pretty easy. You just sum up all the forces. Plus 150 minus 600 plus 100 minus 250, and you get a minus 600 Newton meter force in the j direction at point A. To do the moment calculation, you have to take the sum of all of the moments of the four forces, where the first force, 150 newtons, acts at point A, so it has 0 moment. The second force then will be a minus 600 newtons crossed with a 1.6 in I direction position vector. The 100 Newton force in the plus j direction will be crossed with 2.8 I position vector because it's 2.8 meters to the right of point A. There's our second term. And our third term says that a minus 250 Newton force in the j direction gets crossed with the full length of the beam, which is a 4.8 meter times I position vector. And we do this simple multiplication. All of them will create a moment vector in the k direction, and we get minus 1,880 Newton meters in the k direction is the equivalent moment at point A, denoted by the symbol m sub a and r as a superscript. The moment is a negative sign because it's a clockwise moment. In step 2, we define a force couple system at B that is equivalent to the force couple system at A. The force R remains unchanged. It's going to be minus 600 newtons at A, and it's going to be minus 600 newtons at B. We just need to figure out how do we convert this minus 1,880 Newton meter in K moment at point A to move it from point A to point B. In this case, we use the notation m sub b of the resultant forces is equal to m sub a of the resultant forces plus the vector BA crossed with R, where R was minus 600 newtons in the j direction, and vector BA is equal to minus 4.8 meters in the I direction, because point A has x equal to 0, point B has x equal to 4.8, and 0 minus 4.8 is minus 4.8. So minus 4.8 in I crossed with a minus 600 newtons in J becomes a positive 2,880 Newton meter moment that gets added to the original minus 1,880 Newton meter moment. And that gets 1,000 Newton meter moment acting in the counterclockwise direction at point B. In step 3, we get to find the location for force R so that the moment of R about point A is equal to the resultant moment m sub a. Small r cross large R has got to be equal to the resultant moment m sub a. Vector r is x in the I direction, where x is just the value along the beam going to the right. The resultant, capital R, is minus 600 newtons in the j direction, and that has to be equal to minus 1,880 Newton meters because that's what the moment is on the left side of the beam. So we get minus x times 600 newtons in K is equal to minus 1880 Newton meters in K. Doing that simple math, x equals positive 3.13 meters, which means if you put the force F equal to minus 600 newtons exactly at 3.13 meters to the right of point X, it has the same effect on the beam as our original four forces.